All right, ladies and gentlemen, thank you for joining us. My name is Chris Stewart. I'm a science communicator and I'm the host for this evening's broadcast. Thank you for joining us for the second live online lecture as part of the University of York's Open Lectures program. Before we get into the details of this evening and before I get a chance to introduce our speaker, a few technical notes. If you're watching live, you can ask questions at any time using the Q&A button down the bottom of the Zoom screen. Now, that doesn't mean that you'll be able to sort of stick up your hand and interrupt the speaker. We'll be keeping those questions for later on, sifting through them. We can't guarantee that we'll get to all of the questions, but we'll do our best to sift out as many as we possibly can. Should you have any technical issues, should your Wi-Fi drop out, heaven forbid, you can always rejoin using the link that you got when you signed up to join us for this event and come back in and rejoin the lecture then. And also remember that the event's being recorded. We're going to be putting this out there onto the interwebs for you to watch later on at your leisure. So that's all the technical stuff. I hope none of that is absolutely necessary. I hope you just enjoy the show for the rest of the evening. On to the show. Tonight's speaker is a lecturer in the Department of Physics, the Physics Department at the University of York. She's also director of the Astro Campus at the university, which is a teaching and learning space with a whole bunch of telescopes and teaching facilities on campus. And tonight she's going to be doing something which actually Emily and I do quite a lot these days. The reason for that is because Emily and I have a podcast together. Yes, this is a little plug. I'm just going to get that in there nice and early. We do a podcast. Who doesn't do a podcast under the current lockdown conditions? We do a podcast every week called Syzygy, in which Emily talks about all sorts of fascinating things to do with the universe, the cosmos, and astronomy. And my job in that podcast is to kick back, let her talk about fabulous things in the universe, and then try to ask intelligent questions. My job's made much easier tonight because all of you at home listening to this will be throwing in the questions that I can ask on your behalf. So see if you can come up with some good ones and hit that Q&A button down at the bottom there. But tonight, Emily is going to be talking about her own particular personal interest in research, which is asteroseismology. Now, one important thing, and if you're struggling for a question, you might want to throw this one in. That's astro with an E, not astro with just an O. So you could ask her the question, why is there an E in asteroseismology? Anyway, to tell us all about it, please do make very, very welcome. I guess I'd normally say in the usual fashion of banging your hands together, but we can't hear you. Feel free to applaud anyway. Please make her very, very welcome, Dr. Emily Brunsden.
Hello. Thank you very much, Chris, for that introduction. Yeah, we've been running Syzygy for a couple of years now, and it's been such a fantastic experience getting to learn about lots and lots of different areas of research in astronomy. And that's been amazing, and I've learned so much along the way. But I'm here to tell you tonight about my own personal research, which is, as Chris says, in the field of asteroseismology. Now, I've got a presentation that I am sharing. And I'm going to talk through this presentation today. So I'll give a couple of seconds for that just to load. So my research field, which is in the talk topic for the title for the talk tonight, is the music of the stars. And this was indeed the title of my thesis. And it's a title that I have used ever since because it so well describes the specific types of physics that I'm interested in looking at inside of stars. So I'm going to start off by explaining kind of the overall goals that we have. What do we actually really want to find out? What's the end point, if you like, of this particular field? And it's a pretty large field altogether. And that is to study the pulsations in stars in order to figure out what's actually going on inside a star, what's going on into the inner regions all the way down to the core of the star itself. Now, that might seem like a fairly interesting question and maybe something that we should be able to find out fairly easily, but it doesn't take too long to go along the train of thought to think about, well, hang on, stars are first of all incredibly far away, right? Most stars are only tiny, tiny pinpoints of light. We can't even tell that they've got a top and a bottom in even some of the best telescopes in the world. Yet we want to not only find out what's going on the surfaces of stars, but we want to find out what's going on way down deep into the interior. And we can't just send space probes down into stars that are tens of millions of degrees, fusing hydrogen to helium, burning away inside their cores. We just don't have a way to do that. So what we need to do is use some other tools and techniques that we have available to try and figure out what's actually going on inside of them. Because knowing what goes on inside a star is everything. It's going to tell us everything we need to know about how that star works, what actually fusion reactions are going on, how fast are they going on, because all of those things then go on to determine what's the whole life of this particular star going to be. Now, the way that we can do this is by using information that we get from the surface. So we do get quite a lot of information from the surfaces of stars. We don't often, we can't usually resolve them. We can't usually say that's the pole of the star, that's the top, that's the bottom, that's what's going on in the middle. There's only a very, very few, very, very close stars that we can do that with. But with most stars, we can see their surfaces because their surfaces are putting off light. And that light is what we're going to be using as our primary tool to figure out what's actually going on. And it turns out that many, many stars pulsate. So the light that we get from them changes, and I'm going to tell you lots of different ways that that light changes. But these pulsations change the surface of the star. They kind of make the whole surface really wibbly wobbly. And the picture I've got here, which is on the left-hand side of the screen, is sort of the wobbly surface of the star. This is a hugely exaggerated picture, but it kind of gives you an idea of the fact that the surface of a star isn't just a uniform, smooth ball. It's actually, there's lots of interesting physics going on, lots of waves are created. So coming all the way to the top in our word asteroseismology, we can sort of break it down. I mean, first of all, asteroseismology is a great word. It scores you an awful lot of points in Scrabble, though how you collect so many vowels, I'm not really quite sure. But if you are able to do it, it's a really good one. But if we just broke it into two, there's two sort of fairly familiar words in there. There's the astero, which relates to sort of the celestial bodies or even stars specifically. And then there's seismology. And you might have heard of seismology before in the context of looking at seismology of the Earth, looking at earthquakes, for example. So earthquake studies are the studies of waves in the surface of the Earth, and you can figure out actually quite a lot about the surface of the Earth using studies of earthquakes. And if we then take our new prefix that we've added to that, which is the astro, then we're now looking at the study of waves in celestial bodies, and in particular the study of waves in stars. And so it's these waves that give them these pulsations that we're now able to study and find out lots and lots of different things about the interiors of stars. So that's kind of the whole of my research field in a nutshell. Now, I'm going to take you into the detail of that and give you some insights to how far we've managed to get along this journey of being able to figure out what actually goes on inside of stars. But to do that, I'm going to sort of start at the beginning. And the beginning is when, just over 100 years ago, physicists and astronomers started to think about how do we actually construct a model? How do we build up a picture of all the different bits of physics that are going on and how a star actually works? And one of the most famous stellar physicists at the time was Sir Arthur Eddington. And he did an amazing amount of work looking at models of stars, trying to understand how they actually operated. And his sort of seminal work, his most famous book, is called The Internal Constitution of the Stars. And stellar physicists today recognize this text as one of the foundations of our entire field. And so I picked up this quote from within the textbook. It's where Arthur says, "What appliance can pierce through the outer layers of a star and test the conditions within?" And this was a kind of rhetorical question. He didn't really have an answer. In fact, in the 1920s, there was just no way of imagining any way that we could, in the future, be able to actually test and measure the interior layers of stars. We just would have to rely on physics and models and equations to figure that out. But however, less than 100 years later, I can give you a bit of a feeling for actually we are getting pretty good at doing this now. And we can actually use asteroseismology as the appliance in which we can pierce through these outer layers. So I'm going to take you back to the title again, because I've called this talk The Music of the Stars. And I haven't said anything about sound, and I haven't said anything about music yet. But it turns out that I have said the joining factor a few times, which is I've talked about waves. And if you know a little bit of musical physics, you might have noticed that music is built around the concept of waves. So when I speak, what's happening is that I'm actually creating pressure changes in the air. Those pressure changes travel through the air. And in this case, they're being picked up by the microphone on the computer, but then your computer is then putting that back out, and your ears are picking those waves, those pressure changes up and transforming them into sound in your brain. So it's all about waves. And then the different noises, the different sounds that you hear are based on different properties of the waves that are being produced. And musical instruments make very, very clever use of waves in order to make sound. So I'm going to play you a few notes, first of all, and tell you a little bit more about what's going on in terms of the waves that are being produced by these different notes and different musical instruments. So the first thing, I'm going to be playing you a note. I'm not a very talented musician, I'm afraid myself, but I did check. I'm going to play you a single note. And the particular note is the B above concert A, if you are a musician. So I'm going to play this note. I will just play it one more time, just to make sure that it's nice and clear. So that note there is being played by a violin. Now, if we were to play this note again, but play it on exactly the same note, but we play it on a different instrument, it sounds a bit different. So now I've got it being played on a cornet. So there's a clear difference between the two instruments. Even though they're playing exactly the same note, they sound different. You can tell that one's being played by at least a string instrument and one's being played by some kind of brass instrument. Now, if you ask a computer to play this note, this is what the computer would play. So there's not really much richness at all in that sound. So how does exactly the same note sound different when you've got different instruments? Well, what's happening is that because of the nature of the instrument, it's not just actually playing a single note. So the graph that you're looking at here, this is the graph of all the different frequencies of sound that are being produced by, in this case, the violin. Now, this note that we're playing, this B, which is just above concert A, is at 497 kilohertz. So 497 hertz. And what that means is that you've got a wave which is vibrating at 497 times per second. And if you see that peak where the number 1 is, that's exactly what that frequency is. But the violin doesn't just play that, it actually plays harmonics, which are multiples of it. So it plays twice that frequency, 3 times that frequency, 4, 5, 6, 7, etc., all the way up. And so all these harmonics, which are all the different peaks in the graph, are being played by the violin, even though it's playing a single note. Now, the heights of those peaks you see are kind of varying. So in this case, we've got the 4 and the 6 are a little bit higher, say, than the 3 and the 5. And that's the part of the note, that's the part of the instrument that's really unique. It's a fingerprint, and for every individual musical instrument. Violins will have similar spectra, but every violin will have very, very slightly different peaks. And so if we were to look at the cornet, then it would excite slightly different peaks, would be slightly different heights. So it would play a slightly different note, and we hear that as being slightly different. So that's kind of how music works. You put together these different sounds from different instruments, and you can build up to a piece of music. Now, how on earth is that going to relate to stars? Well, first of all, stars work with waves, but not quite in the same way as musical instruments do. They have waves on the surface. So I'm going to step you through kind of how we look at waves in 3 different dimensions. The first wave dimension that we can look at is 1 dimension. And this is what you might see if you have a wave on a string. So I've got an animation here. I've got a string which is fixed at each end, and these are lots of different waves or lots of different harmonics which you can actually excite onto the string. So one way, for example, to think about this would be the violin. If you vibrated the violin string, you can set that up to have lots and lots of different types of waves, depending on where you pluck the string and where the motion is going to be along the string. So we can have a wave with lots of different harmonics in one dimension. Now in two dimensions, this might be something like, for example, the wave that you see on a drum surface. So here you can imagine we've hit the center of the drum, which is affixed all the way around the edge. We've hit it in the center quite firmly, and it's now vibrating in a two-dimensional surface along a plane. But there's lots of different ways that you can set this up. You can set this up like this one, where the center moves up and down, and then you've got another sort of ring, which is about halfway moving up and down. Or I've got another example here where you can set up a drum moving with the center stationary and lots of pulses up and down as you go around the drum surface. So you can do lots of different things, and these would generate different types of sounds. And then the final way we can imagine waves is to then take this same maybe drum surface or 2D surface and stretch it round into a ball. And when you do this, then you get a sphere which is pulsating. So now we've got waves, but they're now traveling around a surface of a ball or indeed a star. So this is, for example, a mode of pulsation of a star. You can see that some parts are moving in and some parts are moving out. But overall, the star is there's got some fixed points like the top and the bottom of the star. So there's lots of these different modes that you can have and you can excite. I'll show you some more examples that we do see excited in stars. But it's all based on wave physics. We've just taken it from the one-dimensional string up to 3 dimensions for a star. So we've now got some idea of how music uses waves to create different notes. And we've now got waves which can be created in 1, 2, or 3 dimensions. So let's put together what maybe a piece of a star might be doing in terms of pulsation and how that relates to music. So the first way we might want to measure a star that's pulsating is to look at its change in brightness. So this is, we make one measurement across the whole surface of the star, which is how bright it is. And we can say that that brightness for a pulsation will change over time. Now, over the last sort of decade or so, we've become extremely good at measuring the brightnesses of stars. And it's thanks to people who have worked really, really hard, particularly in actually the field of exoplanets. So I've got a picture here on the left of the Kepler Space Telescope. The Kepler Telescope was really popular planet hunter. You might have heard of it. It's found, I think it's coming up to around 60% of all the exoplanets that we know today. So about 2,500 exoplanets. And the only way it did that was it was able to measure very, very tiny changes in the brightnesses of stars. Now, asteroseismologists and people working in pulsations were also part of this group, because it turns out you want to measure very, very tiny changes in the brightness of stars. That's useful to work in pulsations as well. So Kepler was an incredibly successful mission, and I think now we've really moved on into a new era. Kepler finished observations in 2009, and for just over 2 years now, we've had Kepler's successor, which strangely doesn't quite seem as famous, and that is called TESS. So this is a picture on the right. This is TESS. TESS is also a space telescope. Instead of being, Kepler was pointing at kind of one little patch of sky, TESS is actually doing an all-sky survey, and it's operating as we speak. It's just finishing up its first 2 years of data gathering. And once again, TESS is one of these telescopes that's measuring exquisitely, beautifully, very, very tiny changes in brightness. For people who study planets, they're looking for what happens when a planet passes in front of the star. You get a very, very small change in the brightness. But when we're looking at pulsations, we also want to measure very, very tiny changes as well. So I'm going to show you a graph of one of my favorite stars. it's not got a very, very beautiful name, I'm afraid. It's called TIC 219234987. But what this star is doing and what this graph is showing us is that it's changing in brightness. So the red line shows you the brightness over time. The time on the bottom axis there is measured in days. It's just kind of a random zero day. And the y-axis is showing you how bright the star is. So you can see that there's something quite regular going on. You can see it's going up and down and up and down and up and down. But the heights are changing all the time. You get some, particularly towards the end, where you get really, really intense brightness, and then it drops down to very, very low brightness. So this is an example of a star that's pulsating. It's not just pulsating with one frequency or with one note. It's actually got quite a lot of notes all mixed up together. And that's what's causing this kind of jumble of irregularity. There's several notes overlaid on top of one another. So that's the first way we can measure the pulsations in stars. The second way, which is the way I do most of my research in now, is actually using the color changes of the stars. So just like stars change in brightness over the course of their pulsation, they also change very, very slightly in color. Once again, this change is really, really tiny. So it's only been in the last 20 years or so that we've been able to have the technology to be able to measure these tiny changes. But what happens is when you have a pulsation, and I'll play you a little movie of a pulsation again, is that you'll notice that part of the surface of the star is moving towards you, and then it changes, and then that part of the star moves away from you. And when you have a surface which has got light coming from it, and it's moving towards or away from you, that actually changes the color of the light. So when the surface is moving towards you, what happens is, this is the Doppler effect, the light becomes a little bit bluer, and when that part of the surface moves away from you, the light becomes a little bit redder. So we can monitor those changes and watch the star sort of go from very, very slightly blue to very, very slightly red, back and forth and back and forth. And we can measure the pulsations in this way as well. So this is what I've been involved with mostly over the last few years. And I've been doing observations from New Zealand. Some people may have picked up that's where my accent's from. So I've been working in the Southern Alps of the South Island of New Zealand on a telescope there. And we've been measuring these color changes using a technique called spectroscopy. So there's a picture of the telescope there. If you're any Lord of the Rings fan, you might recognize some of the backdrop there as the plains of Rohan, where some of that was filmed as well. So it is a really stunning part of the world, and we have access to some really amazing telescopes down there. So we can measure the changes using brightness changes, or we can measure the changes using color changes. And both of those give us complementary, but also quite different sometimes information. We can probe different parts of the star using these two techniques. So what do we actually see? Well, if we took that, let's say that the light curve, the red curve that I had before, and we measured the frequencies of those pulsations. So I've put here two different graphs. The top one in the blue is a graph of one of the stars that I've been studying. And the bottom one is our violin spectrum, just to remind us kind of what these graphs look like. So in the top one, we've got a star. It's got some pulsations with different frequencies. You can see there's a really, really big pulsation, which is occurring somewhere around 1.2, 1.3 times per day. Now, this is a very, very different frequency to the frequency of sound that we can hear. Remember, I was saying that we were listening to notes that are kind of around 500 times per second. Now we're talking about something that's going maybe only 1.5 times in a day. So if we wanted to listen to the sounds that we get from these stars, listen to these frequencies, then we do need to kind of transpose them into something which is within our audible hearing range. But you can see the similarity in the graphs. Indeed, there's something at 1.3, 2.3, 3.3. These are the harmonics that are being produced in the star. But there's also something going on that's quite interesting at about 0.7. So there's lots of different bits of information that we can pull from these kinds of frequency analyses. So one way to think about it would be that every single frequency that we can pull out from a star is analogous to a different musical note. And we can put those together and we can start to generate either a song perhaps, or indeed we can start to generate what actually the physics is going in the star. Because each of those frequencies has an independent different mode. So I've shown you one example of a star pulsating, but there's lots of different ways geometrically that they can pulsate. Here's an example of a star that's going quite crazy, not just sort of side to side, but also up and down at the same time. So this is one example of a mode that could be associated with a frequency. And here's another one. This is actually probably the most boring mode, but this is the most popular note. This is the most popular frequency mode that we see inside stars. It's kind of just a swaying back and forth. It's actually one of the simplest ones, so maybe it's not so coincidental that it's the most common one that we see. So once we have all of these modes, we can start to build up a picture of what actually is going on inside the star. Because we have to remind ourselves that these surface pulsations aren't just happening on the surface. The reason they exist is because there's lots of interesting things going on inside the internal structure of a star. So here I have a little movie of an example of, you've got the surface of the star, which is the red, smooth sort of surface, and that's pulsating. But we've cut away into a kind of segment here. And so you're seeing inside the star. And now we're going all the way down into the core. And this is the core of the star, which has got some pulsations going. And then those pulsations are propagating out through the rest of the surface of the star. So what's going on the surface is completely dependent on all the internal physics. It's dependent on things like what the speed of sound is inside the star, what's the internal temperature, what's the internal pressure. All of these things will change how those surface pulsations manifest themselves. So let's look at a couple of examples. Now, I'm going to make a confession at this point and say, despite the fact that my research is called The Music of the Stars, it turns out that stars are not particularly musical. In fact, they don't seem to have heard of things like scales, or what notes go together nicely, or what kind of rhythms might work quite well for those notes. So every time I transpose some of the frequencies that I see in stars into, to try and put some music together, try and make a song, it turns out really awful, in fact. So maybe some stars could learn a little bit from our musical theory. But I'm going to show you some examples. So the first one is actually the sun. So the sun pulsates. It's pulsating at a much, much higher frequency than most of the stars that I look at. It's pulsating something like once every 7 minutes. So it's a reasonably fast pulsation, but it's very, very shallow on the surface of the star. So it doesn't go very, very deep, this particular pulsation. But what we can do is we can take that and match it to So those were some of the sounds taken from the data taken from our sun. So one would ask, well, what have we learned from these pulsations? What have we learned from the song of the sun? Well, we've actually found out something really, really interesting about our own sun. We've been able to look at the surface for hundreds of years, in fact. We've been able to see the surface of the sun, and we've been able to track how the sun rotates. And up until recently, the way we've been doing that is, say, by watching sunspots travel across the surface of the sun. And we've known for a very long time that the surface of the sun does something quite unusual. It actually doesn't all rotate like a solid sphere. It turns out that the sun rotates much, much faster at the equator than it does at the pole. So it takes about 26 days for the equator to go around once on a rotation, but the poles take about 36 days. So I've got a little cutout here of the sun, and this is going to tell you what the brand new results that we have from looking at the rotation profile of our sun. If you can imagine, this is kind of a quarter of the sun, where the curved surface represents the surface of the sun. And we've got the red area, which is at the bottom of this graph, and that's the fastest area that's rotating. So that's towards the equator. And then we've got the purple and purpley black area at the top. That's the pole of the sun. And so that's the slowest part that's rotating. And then as we go in towards the bottom left-hand corner, this is going deeper and deeper into this interior of the sun. Now, up until recently, we haven't been able to make any measurements beyond the dashed line. The dashed line kind of says this is what our measurements were able to do up until we had what we call helioseismology, or the study of the pulsations in the sun, helios being the sun. But what we were able to do is use those 7-minute pulsations to actually figure out something's going on deep inside the core. And it looks really interesting because all the colors basically of this map that's below the dashed line, it's pretty much all the same color. Even though on the surface you have quite a distribution of rotation, inside the sun seems to be rotating all at the same speed. So what that means is you don't have to actually go very, very deep. It's something like 25% the depth into the sun. And actually the whole sun is rotating like a solid object. And it's just the surface that has this really interesting pattern of the equator rotating faster than the pole. And that was very, very surprising. We thought that actually that pattern should continue at least a lot deeper into the sun. But now we know that the sun rotates as a solid core, then that actually changes quite a lot of the interesting physics that we can do to figure out how the interior of the sun works. So this was a really, really important result that came out just recently from helioseismology. So this is really, really great. This is showing that, you know, pulsations on the surface can tell us something really interesting about the interiors of our own sun. So of course we want to apply this to stars, to all types of stars. Unfortunately, it's not quite that easy. So some types of stars we've been able to make great progress with. And I'm going to show you an example of one of those now. But there are some types of stars that are proving to be a little bit trickier. So we want to understand the whole process of stellar evolution. That's how stars are born, how they live out their entire lives, producing light and energy, and then eventually how they die. And that whole process is determined by what goes on in the interior. So we need to understand the pulsations on different types of stars at different points in their lifetimes in order to be able to kind of map what happens to the interior of a star from the moment it's born all the way till its death. Now, it turns out we've got some really, really good examples here. So I'm going to play you a video, and I'll give you an upfront so you know what you're going to be listening to. We've got 3 different types of stars that we're going to hear a little bit about. Here are 1 or 2 of their pulsations. So the first one is, it's called a dwarf star, but what it really means is a star like our sun, it's in its main part of its life, right? It's merely fusing hydrogen to helium, and it's kind of in the ordinary part of its existence, middle age, if you might say. Now, then we're going to see 2 later parts of its life. So then we see a stage called subgiant, which means that basically the hydrogen's starting to run out. The star's going to have to do something else in order to keep itself going for a little while. And then it eventually becomes what we call a red giant, which is a very, very large puffy star towards the end of its life. And these 3 stars all have pulsations, and they all have slightly different pulsations. So I want you to see if you can listen to the differences to these 3 as we go through the video. audio was strong enough for you to be able to tell. If you couldn't, then you sort of had, for the dwarf star, we had a sort of deep sort of rumbling sound. So that's for a star that's on the main part of its life cycle. Then as it evolves, it becomes larger, and the pulsations start to become slightly higher pitched and even kind of more like a hissing, crackling sound, until we get to the red giants, where they really become this sort of hiss sound. And those pulsations in red giants is actually one of the main breakthrough areas that we've had in asteroseismology, where we've been able to make enormous progress into determining lots and lots of really important information about a star. Until we had asteroseismology of these stars, then if you wanted to measure, say, the mass of a star or the radius, then just a random individual star in the sky, then you're probably looking at having an error which was maybe something like up to a half. So if you thought that that star might have been, you know, twice the size of the sun, you would have to say, but we're not sure, because it might be, you know, 2.5 times the size. You'd have really, really large errors in all your measurements. But with the asteroseismology, particularly with these red giant stars, we're now able to get masses and radii which have errors less than 5%, which is incredibly accurate for stars that are hundreds, if not thousands of light years away. What's really exciting about that is that we can do something even better, is that we can measure the age of a star, which is an amazing thing. We've never been able to measure age particularly accurately for stars before, but we can now measure ages of these stars to an accuracy of something like 10%, which is totally revolutionizing our understanding of how stars go through their life cycles. A really, really exciting sort of side part of that too is that astroseismologists have now become planet hunters' new best friends, because the planet hunters sort of said, well, yeah, sure, it's fine. You can use our space telescopes, you can do your pulsation work, and we'll do our planet hunting work. But it turns out if you want to know anything useful about an exoplanet, then you need to know a lot about the star. Because remember, all the light that you get from a measurement comes from the star. So if you want to know your planet's mass, if you want to know how big your planet is, if you want to know if it's a gassy planet or if it's a rocky planet, you need to have really, really good information about your star. And so astroseismologists have become sort of, I guess, great heroes in terms of planetary science as well, because we're now able to make these super accurate measurements, which now say, well, instead of having a, you know, an Earth twin, which might be 2 times the mass of Earth, or it might be 4 times the mass of Earth, we just don't know. We can now say that to accuracies of something like 10%, which is really, really incredible, and helping us learn a lot more about planetary science as well. So we've become kind of best friends, the planet community and the astroseismology community, which is really, really nice, because it's nice to work with lots of interesting different parts with your research. So the last thing I was just going to say is kind of looking forward to the future. So it kind of almost sounds like we've summed up this whole thing of astroseismology. But what I've been very careful is to sort of talk about is I've talked about some of the great new results, but they are for particular types of stars. We've made great progress with the sun, and we've made great progress, for example, with these red giant stars. But there's a lot of stars out there. There's a lot of groups of stars out there that we're trying to work really, really hard to figure out, are there different ways that we can analyze their pulsations? The types of stars that I work on, for example, are stars that are pretty similar to the sun. They're just a little bit bigger and a little bit hotter, but none of the physics that we've been able to use for, say, the red giant stars works. The observations aren't the same, the stars aren't the same. So we haven't quite cracked that particular code just yet. So we're working pretty hard on those sorts of questions. So to finish off with, I would say that astroseismology is definitely looking up. We've got amazing space telescopes that are running right now, like the TESS, which is the little picture up on the left. We've got new missions which are under development. This is a picture of Plato, which we hope to launch in the 2020s, another follow-up space telescope. And the bottom large photo is actually a photo taken by one of my students who was working in New Zealand last summer, or New Zealand's winter, last UK summer. And he was working on the telescopes down there and helping us make amazing observations of brand new stars that we discovered with TESS. that we're hoping to crack and hoping to nail to see if we can actually figure out what is really going on inside of these types. So to conclude, hopefully I've walked you through kind of the field of asteroseismology, why we want to study pulsations, and indeed why determining their interior structures is so important. So I will end my presentation here and say thank you very much for your attention, and I hope there's some fantastic questions in the Q&A.
Thank you very much, Emily. I think that was just brilliant. I love the fact that you managed to actually even get in there the astronomy is looking up joke again. It's, at the end of a talk, one normally sort of says, can we have a round of applause for our speaker? Feel free at home. And if that means that your neighbors get all confused and come out the front and start thinking that we're, you know, a day or so early for applauding all our frontline workers, that's okay. I'm prepared to take that risk. Listen, we do have some time for some questions. We have, you know, anywhere up for sort of 15, 20 minutes. And we have a bunch of questions which have come through from our audience. I'm just looking at the numbers down the bottom of my screen. Emily, we've got about 600,000 people that have tuned into this online lecture. So I think we've done very, very well. I've got a couple of questions, but I'm going to defer to the audience first. I think that's only reasonable. So look, the first one that came through, one of our audience members by the name of Panos, I hope I'm pronouncing that correctly, Panos, took us up on the offer of the first question being, can I take a guess? Is it Astero with an E because the name comes from Asteria, which means in Greek, the stars. Is that true? Can you confirm or deny, Emily?
That is, yeah, it's pretty much on the mark. So there are two stem words that come from Greek and Latin, and the lines do blur a little bit between the Greek and the Latin as far as I understand. So there are two stems. There's Aster, A-S-T-E-R, and there is Astron actually, A-S-T-R-O-N. You see Aster used for things like asterisk, which is a star, and Astron used, for example, an astronaut, which is a sailor of the heavens, I think is kind of a literal definition. Yeah, so they just have two different stems. It tends to be more that Aster refers to stars, although I have heard that refuted, but yeah, two different roots. Let's just call them celestial bodies.
All right, fair enough. Thank you for clearing that up. So one of the other questions that's come through, which is similar to one that I had actually written down myself. So I'm gonna give the listener the credit for that one, but we were on the same wavelength there, which is, you were talking about being able to measure, you know, the wobbles on the surface of the star. I'm going to call them that, they're wobbles, but also being able to measure the differences in speed, the Doppler difference, you know, the red or the blue. Emily, I'm sorry, I'm going to call you on this. Those have to be incredibly small, right? And so our listener Neil has asked, like, how do you do that? How do you measure? How accurate are these telescopes? How accurate are these observations? How do you do that? How do you measure so precisely?
Yeah, it's an amazing question. And it's honestly something that I still have to sometimes take a step back and say, yeah, we're doing this. This is amazing. So what we've been really benefited from, again, is a huge jump in technological progress, particularly to do what's also linked to measuring exoplanets as well. We can measure now changes in the colors, if you like, that come from changes in the surface down to, for my stars, I'm talking usually about 100 meters per second change. So that's a velocity change. So that's how fast the surface is moving backwards and forwards. We've only been able to do that for, I guess, maybe about 10 years with our current technology. But where we're going, this is even getting more exciting, is that the newest planet hunting telescopes are now able to look down to centimeters per second.
That's
so we
amazing.
can measure the surface of a star moving down to the centimeter per second. Which
Sorry,
is
can I just check, how big's a star?
Yeah, large.
That's insane. Okay, well done all in your field. I think that deserves another round of applause. Next question is from Frida, who says, how do you select which stars to focus your research on? I mean, correct me if I'm wrong. I may be wrong about this. there are quite a few stars out there. So how do you choose? How do you choose which ones to observe?
That's a really, really good question. So what we do is we tend to fall into groups. So I work in a group working on a group of stars called Gamma Doradus stars. And how these stars are grouped is usually by where they are in their lifetimes, how big they are, and how hot they are. And then from that, you'll get a particular type of pulsation or a particular set of frequencies. So I study these Gamma Doradus stars. They have very typical frequencies of around kind of a few hours to maybe a couple of days. And then we sort of, in my subgroup, there'll be a few tens of astronomers working on mostly those stars. And we identify them by, first of all, by getting information from these very, very big surveys. And that's where TESS is really, really helpful because it's scanning the whole sky. So if we find a star that kind of matches that, we can pop it in our group and of stars, and we go off and do some more detailed observations. So at the moment, we've got on the order of about 60 or 70 stars that fall into our group that are really good for us to follow up on. But we do know of many, many fainter ones. So there's probably, I don't know, a few hundred in total, maybe 1,000 all up in this particular group.
All right, thank you. Next question is from Jim. Jim says, do the gas giants rotate like the sun, poles slower than the equator? Now, just taking you back into your talk, right? You showed us that the weirdness of the rotation of the sun, with the poles are not rotating as quickly as the equator. But the sun is, I mean, you called it a dwarf star, which makes it sound fairly sort of cold ordinary, but huge. I mean, gas giants, the red giants and these are enormous, absolutely enormous stars. So do they have similar kinds of rotation patterns? Do we know?
Yeah, it's a very difficult thing to measure. We do have some stars that we have measured this kind of change in the rotation because we've been able to measure star spots. So like sunspots, we've been able to measure spots on other stars. The red giants, yes, they are some of the types of stars that do show this change, although not all of them, at least to the precision of our measurements so far. So I think there's more to be done in that kind of area.
Well, that's handy for you, isn't it? And your research grants. I'm going to go into our listener Panos has come in with a whole bunch of questions. So I think it's only fair to go to another one, given that the first question wasn't really a question; it was actually answering a question that we had asked. So Panos's next question is it's about magnetic fields. We know that the sun has pretty extreme magnetic fields. So what's the relationship between the magnetic fields of the stars and the way that they pulse? Is there a relationship there?
Wow, yeah, that's a fantastic question. And it's complicated is actually the short answer, but I will give you a longer answer. So some types of stars have stronger magnetic fields than others. Actually, the sun, despite us thinking it's got a strong magnetic field, it's pretty tiddly in terms of kind of the star sort of populations.
I'm getting a sense that the sun isn't nearly as interesting as we all think it is, Emily. Come on.
There's no seismologists in the audience.
Sorry, carry on.
Yeah, so it's, in terms of stars, it's not that great. And in fact, it doesn't have a huge significant effect on its pulsations. But there are stars that have insanely strong magnetic fields that rotate quite slowly and actually have very interesting interactions between the magnetic field and the pulsation, such that they directly connect and they talk to one another, if you like. The magnetic field controls and excites the pulsations.
It's all very complicated. All right, so we've got time for another several questions. Let's work our way through it. Question from John, going back to, so you played some audio, which I don't know about anyone else watching at home, that came through quite strongly on my headphones here. Some audio where you had translated the pulsations that you'd measured. As you say, those things are generally happening far, far slower than anything that we could hear if it were turned into an audio signal. And so you need to transpose those up. And the question that John's asking, if I'm paraphrasing, I hope I've got this right, John. Is there a standard way of doing that? Is there a standard tuning, if you like, for turning the pulsations that you can record from stars that you observe into a human audible frequency, or do people just tend to make that up for the benefit of an interesting YouTube video?
Yeah, that's yeah. It tends to be more that people do just select how they need to scale it in order to be able to get something that's actually audible. Because even if you scaled all of the frequencies by the same amount, that doesn't necessarily mean that they're all going to fall into the range of human hearing. So for the general purposes of kind of creating a nice new piece of music, or not very nice piece of music as they turn out to be, it's pretty ad hoc. Although I am aware of some people who have visual impairments who tend to work in audio space. So instead of looking at graphs and things like that, they'll tend to listen, and they're much more kind of systematic about how they'll do it, because they want to be comparing different stars. So you've got to do the same process to different stars in order to be able to hear the differences.
All right. Okay. Thank you. Another question. It's probably one of the most basic ones, really, I think, which we probably should have started with this one at the very beginning, which is, why exactly do stars wobble and pulsate like this? What causes that? What sets up these crazy motions, these dance moves that you showed? Where do they come from?
Well, it's a good question. So the interior of a star basically gets out of balance. So it can be, usually occurs in a very, very specific temperature, pressure, etc., kind of sort of series of parameters. And then what happens is that it gets out of balance, and so the star will have a bit that's contracting, but it will contract a little bit too far, which means it will heat up a little bit too much. So then it has to expand, and then it will expand just a little bit too far, so it's a little bit too cool, and then gravity will pull it back in. And so you get this kind of cyclic oscillation. It's kind of, it's a wave that it can't get out of, because it keeps overshooting the neutral point, if you like, once it's set up.
Questions. Sorry, I'm laughing because I can see the questions coming up as you're talking. Someone at home, Cheryl, has just thrown through a couple of questions. I'm going to go to the second one first. If the astroseismologists are the great heroes, why do the exoplanet guys get all the funding? Do you two know each other? Cheryl and Emily, do you know each other? Is there a bit of a, you said that that you're working with the same data coming from the same satellites and so on. Is there a little bit of argy-bargy back and forth between the two of you? Are you jostling for attention there and funding, or is it very cooperative?
I would say that for a very, very long time, people working on stars were the underdogs. Like, there was no... the general public didn't think stars were particularly sexy. They didn't think, they were going to be solving, big questions in terms of humans, philosophy. So as a field, let's say throughout the 60s to the 90s, it wasn't a hugely well overfunded field. However, then we had planets come in, and all the astroseismologists or planet stellar people thought, well, they're going to get lots of funding because planets are exciting, they're new, they're interesting, everyone loves a good planet. And then we thought, hang on a minute, they're getting funding for all these amazing instruments that we could never afford. Let's just ask if we can kind of piggyback on the back of them and use their stuff. And they said yes. And then we were like, oh yeah, and hey, by the way, we can do this, good research that you're interested in. And yeah, it took off. One of my fun facts, which hopefully there's not too many planet people in the audience, is that there were more papers published by astroseismologists about the Kepler Space Telescope than there were by planet hunters in the end.
Very nice. Look, Cheryl's other question, I think that one was perhaps a little bit tongue-in-cheek, although maybe not. Cheryl says, how did they, that being you, how did astronomers find out the rotation profile of the sun goes flat around the core? You said that the core tends to rotate as one big blob, and the outside does something a bit different. Is there an explanation for that, or is that currently just an observation and some interesting data for models? Have you got some way to explain that?
So I think there's two questions there that you asked. I think one of them is how do you get from the data to the model that I showed you, and part of that's just looking at the pulsations that you see. They have to have come from the interior. They are influenced by what's going on in the interior of the star. And so what you can do is you can set up 100,000 different suns and say, well, which set of parameters is going to produce the star that the pulsations that we're seeing. And so it's a fitting, and you can say, well, okay, it's this one. And that gives you a lot of the internal temperatures and pressures and so on. And so that's what they've been using, along with all the different overtones from these different frequencies, to be able to put together a model of the sun. And then there was a second part, which you have to remind me.
I think you probably actually tied the two of them together. So yeah, I think we're there. I think that's okay. Let's move on. Let's move on. And apologies if I misrepresented that question. Blame me. It's all my fault. Question from Tom, who's watching at home. As the pulsation is based on the star overshooting, we're talking about where the wobbles came from, right? And the star sort of, it goes a bit too far and then it pulls back and it wobbles and it sort of compresses too far and then it bounces back and it just becomes this wobble. Is that going to dampen out over time? Like, does that mean that the stars will just slowly but surely slow down and just become a ball that is sitting there in space? Do these ripples go away?
They do. They come and they go throughout the star's lifetime. Now, I say come and go in terms of timescales of millions to billions of years, rather than sort of on timescales of today and tomorrow. The star's doing something different. So when the star is in the main part of its life, which is the stars that I'm looking at mostly, they're going to be in that main stage of their life for something like 5 to 6 billion years. So we've got a good, perfect time to catch them. But then when those stars evolve and become these red giant stars, their pulsations are going to change because the whole star's changed. It's changed density, it's changed temperature. So the whole physics, therefore, is going to set up a different set of pulsations.
They're inherently big, slightly unstable, wobbly things in space. Yeah, okay. I think I've got that. Listen, we've got time for just one more question, and it's kind of a more philosophical one, I guess, Emily. But we're also coming towards the end of our time. We said that we were going to wrap up at 8 o'clock, and we will keep to that. So, Emily, a quick take on this one, and then we'll finish it all up. Someone watching at home who the only name that I've got for them is CEO. So they're obviously in charge of something, but I'm not entirely sure who we're addressing here. So my apologies for that. But the question is, do you think that the pace of discovery is speeding up? Like, a lot's happened in the last 100 years in science generally, and in your field particularly. 100 years ago, we didn't even know where we were in space. Will the next 100 years, will we find that knowledge is increasing even more quickly? I guess it's a very broad question to you, Emily, of where do you see it going from here?
I would agree that I think the speed of discovery is speeding up. I think a big part of that is the fact that we've got more people who are just purely more researchers in the world, purely more astronomers than we did have, say, 100 years ago, who are working on these things. And the tools that we have available to us, the technology is just going so rapidly. And it's not just kind of the sophisticated telescopes, the sophisticated instruments that I've talked about. It's actually just even basic things like internet and computers being able to do hard sums for us. We're entering now the new age of artificial intelligence and large machine learning computation. This is brilliant for astronomers who have so much data they just don't know what to do with it half the time. So yes, I think we will continue to expand. But just the one other thing I think I will add to that, I think also one of the major reasons we've made so many more strides in the last, say, 30 or 40 years is actually there's more diversity of people doing science generally. I think there's more women, there's more people from ethnic minorities, there's more people who didn't have access, who are providing this kind of different insight, different creativity, different ways of approaching really, really difficult problems. And that's just going to make things go faster and faster and faster, I think.
That's fantastic. Look, we are going to have to call it to an end there, but I think that's a nice place to stop. I'm going to call on everyone watching at home to once again bang your hands together in the quiet of your own living rooms and bedrooms for our speaker, Dr. Emily Brunsdon from the Physics Department at the University of York. Thank you very much, Emily. It's been fabulous talking to you as ever. I kind of feel like we do this often. On that, just another quick plug. Someone was asking earlier, what was the name of the podcast that you mentioned at the beginning? Emily and I, every week, we get together and we record the Syzygy podcast, another name that gets you a lot of points in Scrabble. That's SYZYGY. You can go to our website, syzygy.fm, and tune into the podcast there, or search for it in any of the podcast players. That's enough about us. Listen, this lecture has been recorded. It's going to be available through our YouTube channel in a few days' time, and a link will be emailed to all of you at home who got tickets through in the usual channels. So keep an eye out for that one. In addition to this open lectures program, we're also very, very excited to let you know that the York Festival of Ideas is actually happening. Normally we'd be doing that, you know, in real physical spaces. This time we're doing it via electrons online. We're coming back from the 2nd to the 14th of June. It's going to be a totally online format. Emily and I are going to be there. We're going to be doing a live version of the podcast. So just another plug there. So please do go to the website York Festival of Ideas, all one word, yorkfestivalofideas.com to find out all the details. Lastly, we'd love to hear your thoughts on these events. We want to know, we want to get some feedback. So if you're on the social media in any way, please do throw some comments up there. Let us know what you think using the hashtag York Ideas. If you know what that means, you're all over it. If you don't know what that means, don't worry about it. You haven't missed anything. So that's all from us here at the talk. Thank you very much once again, Emily. Thank you everyone for tuning in. And with any luck, we'll catch you at one of the future events. Thank you everyone. Good night.